In this lecture I want to talk a little bit more about electromagnetic waves. Here we have the electromagnetic wave that you've seen the picture of before, where you got the E field that increases and decreases in magnitude as it oscillates back and forth, and then the corresponding magnetic field transverse to it that's also oscillating. Remember our ratio E over B, right? E over B equals C, so the ratio between these two fields is always the same. We also have here this axis, which is the x direction, which makes this the y, and this the z. So we've got x, y, and z. If you look at this, we've got waves propagating in the x direction. So the E field is sine of kx minus omega t. B field goes as sine of kx minus omega t. K is at 2 pi over lambda. And omega I'm going to write as 2 pi over t. It is also 2 pi f, but the 2 pi over t makes these two equations more symmetric. Energy in this wave propagates in the direction of what's called the pointing vector. And the pointing vector is just the cross product of E cross B. So in this instance, we got E in this direction, we got B in this direction. E cross B points along the x-axis. So this is telling us for these waves the energy flow is along the x-axis, and we've seen this before. In the last lecture we called it the intensity. It's watts per square meter. Remember we had the equation, the intensity is E times B over mu naught, right? And this is the source of that equation. If we look at the energy density in these electromagnetic waves, we'll see some terms that we've looked at before and they still hold true, which is the electric field energy density is 1/2 epsilon naught E squared, and the magnetic field energy density is 1/2 1 over mu naught B squared. E&M waves have momentum as well, and they transfer momentum to objects that they hit. So the momentum, if this electromagnetic wave shown here, this electromagnetic wave is absorbed by something, right? Then the momentum that is transferred is the total energy in the wave divided by the speed of light. If, on the other hand, it reflects, that doubles the momentum transfer, right? Why is that? Well, in the case where it's absorbed, it's like a completely inelastic collision, right? The wave comes in, it hits whatever it hits, it gets absorbed, and then that body has all of the momentum, right? Momentum is conserved, all of the momentum is transferred over into the body that absorbed it. On the other hand, when it's reflected, the wave comes in and goes back with the exact same momentum it had, which means in order to balance the equation after the fact, you have to have twice as much momentum in the object that it reflected off of as you do in the wave. Final bit for an explanation of polarization. Imagine you have a slit in a wall and you've got a rope that's going through it and you're waving it up and down. Now, if you're waving it up and down along the slit, the wave goes through. And on the other hand, if you're waving it side to side, the wave comes to a stop at the slit. This is essentially what polarization does. And the way it works is you have a polarization axis in a piece of material, a filter, and an electric field can be arbitrarily polarized in any direction. When it comes through, the only thing that's remaining is the component in that direction. So if the electric field is making an angle theta with the polarization axis, right, what comes through is E cosine theta, just the component along the polarization axis. If you're wondering how a polarizer is made, it's actually made with long molecules. And what happens is, if the electric field is this direction it essentially doesn't see the molecules because they are very short in that direction, and it takes something comparable to the wavelength for it to be absorbed. However, if the electric field is this way, it sees all of these molecules as something that readily absorb it. So basically, the molecule absorbs the radiation that's in line with it and doesn't absorb the component of the radiation that's not in line with it. After the polarizer, intensity of the radiation past the polarizer goes as cosine squared of the angle. So polarizers reduce the intensity after the fact depending on the angle the incident radiation. Say if it's like this, right? The angle the incident radiation makes with the polarizer. And that's it for this piece on electromagnetics. Till next time.